All right, so now that we've looked at general sequences and series, and we've looked at arithmetic sequences and series, now we're going to focus in on geometric sequences and series. So a geometric sequence is a sequence that consistently multiplies by the same number. We have what's called the common ratio. And the common ratio is the number that each term is multiplied by to get the next term. So it's that same number that you're multiplying each time. So just like with arithmetic sequences, we still have an explicit formula and a recursive formula for how to write the sequence, how to represent it. So the explicit formula is the sequence equals the first term multiplied by the common ratio to the exponent n minus 1. And the recursive formula, we start with a number, and the next term is that number multiplied by r. All right, so we're going to do some examples just to work through that, those different things, how to find them. So we're going to be given a sequence. And we're going to find r, and we're going to find the next 4 terms. And the explicit and recursive formulas. All right, so the first sequence is 8, -2, +1/2, etc. So if you look at this one, it appears that when we see that pattern, if I think about something that's multiplying to get from 8 to -2, I don't really think of multiplication as much. I actually think of division. So I think of this as dividing by a -4. And then -2 divided by -4 would give you 1/2. So anytime you have a geometric sequence where you feel like it's dividing, you can really say that your r value is just a fraction, that you're multiplying by a fraction. So here the r value would be -1/4. You are multiplying by the fraction -1/4. So if we want the next 4 terms, we just need to take the denominator of our fraction and multiply it by -4. All right, and the reason I'm not multiplying the numerator is because the numerator is multiplying by 1 each time, so it's not going to change. So I'm going to keep the one the same. 2 times -4 is -8. -8 times -4 is 32. 32 times -4 is -128. And -128 times 4 is 512. And you don't have to put the negative with the denominator. You could put it on the top, or you could put it on the front. It doesn't matter. All right, so the explicit formula here is a sub n equals the first term times the r value to the n minus 1 power. The recursive formula says you start at a first term of 8, and the pattern is you take the previous term and you multiply it by -1/4. All right. For the second sequence, we're going to say 4, 11, 30.25. I kind of laughed when I looked at the examples that our book used for these, because most geometric sequences, you look at them and you can kind of tell they're multiplying or dividing by something. With this one, I was like, oh, if they hadn't told me, I don't know if I would have noticed that. So one of the ways you'll be able to tell is sometimes within the context they'll say, hey, it's a geometric sequence, so you should try to see what you can multiply to get to the next term. But if they don't tell you that it's a geometric sequence, then you can pretty much count on them being recognizable numbers that you could maybe look at the first couple terms and they'd be some multiplication you'd be familiar with, even though the book gave us some numbers where the R value isn't very nice. So here, if you want to find your R value, you can just divide the numbers. You're going to do 11 divided by 4. And the reason we're doing it backwards, we're going from the second term to the first term, is because I want to see what would have multiplied to get to 11. So if I divide those, then I'll see what you would have multiplied. So it's 2.75. So we're going to say our R value is 2.75, which is strange. And then our next 4 terms are going to be brutal because of those decimals there. So we've got 30.25 times 2.75, and we're getting more decimals. Times 2.75 times 2.75. Goodness gracious. Times 2.75. All right, the explicit formula is the first term times the R value to the n-1 power. The recursive form is the first term. And then to find the other terms, we're going to take the previous term and multiply it. You can put a dot. Well, this one has a decimal. I'm going to go ahead and put parentheses. I didn't use a dot for multiplication because I had a decimal right there and I thought it'd look weird. All right. So that's, once you have the pattern, that's kind of how you work with it to find a formula. We're going to do some other types of examples too, just in case they start to get creative when they ask you questions. So let's say they asked you to find the 27th term of the geometric sequence, and typically when they do this, they'll either give you more than 3 terms or they'll specifically tell you what type it is. They have to give you enough information so that you can see the pattern without confusion. So there wouldn't be like multiple different patterns depending on how you look at it. There would just be the one right pattern. Again, this example has kind of some weird numbers. So what we're going to do, we need to write a formula so that we can find the 27th term. If you write the recursive formula, then you might as well just keep the pattern going 27 times. So what I'm going to do is I'm not going to use the recursive formula because 27 terms sounds like a lot to me. So I'm going to do the work to find the explicit formula, which means I need my first term and I need my R value. And so to find the R value, I'm going to divide these two numbers. 151.2 divided by 189. And the R value is 0.8. And so that means my formula is A sub n equals the first term times the R value to the n-1 power. So if I want the 27th term, I just need to plug in 27. So the 27th term would be 189 times 0.8 to the 27 minus 1. And we get this decimal. And sometimes these can be fraction answers. So I'd always try it, see if you can write it as a fraction so you could write your exact answer. Sometimes the calculator, it's like there's too many decimals in there and your calculator has a hard time. So sometimes that decimal answer is totally fine. Okay, we're going to do one more of these and then we're going to talk about geometric series. So next we're going to find the 12th term if the third term is 32 and r equals -4. So anytime we're messing with arithmetic or recursive formulas, arithmetic or geometric sequences, we typically want to work with the explicit formula just because, like I said before, it can give you specific terms instead of just having to follow the pattern. And so when we see stuff like this, even if you don't know how to approach the problem, as soon as you see they gave you a few different pieces of information, it's like, I'm probably going to need to use the explicit formula. So the explicit formula is the first term times the r value to the n minus 1 power. And then what I'm going to do is I'm just going to fill in all the information I have and see what I can find from it. So I've got the third term. So I'm going to say the third term is, if I plug the first term in and I have the r value and I plug in 3 minus 1. And when I plug all of that in, I should get 32 as the result. So that means that A1 -4 to the second power is -4 squared, which is 16. So we have the first term times 16 is 32. And if I divide the 16 over, that means the first term must have been 2. So I didn't find the 12th term, but I did find the first term. And that's beneficial because now I can write the actual formula. So it's the first term times the r value to the n minus 1. And now that I have the actual formula, I can go through and find the 12th term. So a sub 12 is 2 times -4 to the 12 minus 1. And if we plug that in, we get a really small number, or you could think a really big negative number, which is what makes it so small. So -8 million. Okay. All right, we are going to start some of our notes on geometric series because there are two different types of geometric series that we look at, which is different than arithmetic. When we learned about arithmetic series, we only talked about finite series. We never talked about infinite series. And the reason we didn't talk about infinite arithmetic series is because they're kind of boring. They always either add up to positive infinity or negative infinity. They never add up to a specific number, and that's why we kind of ignored them. But with geometric series, we are going to look at them more in depth because sometimes they do add to a specific number if they're infinite. So a geometric series is the indicated sum of a geometric sequence. And this time, like I just said, we do have infinite geometric series and finite geometric series, and both of those can add up to a sum. Not always, but sometimes. So I'm going to go ahead and give you the formulas for each of those now, but in this video we're going to focus on finite and then we'll focus on infinite in class. So the sum of the first n terms is the first term multiplied by 1 minus r to the n divided by 1 minus r. And then the infinite formula is much simpler. It is s equals a sub 1 over 1 minus r. And you'll notice this s does not have a sub number because it's not a specific number of terms, it's all of the terms. It's infinite. So it's every single term you can think of. Okay, so we're just writing this for now, but we're not going to use it in the video. We're going to do it in class tomorrow. So let's go ahead and do some examples for finite series. So the instructions for all of these examples are just going to be to find the sum. And so the first example is we're going to find the first 6 terms of 8 plus 14 plus 24.5 plus, and then the pattern continues. So for us to find the sum, it's kind of nice to work with this formula as opposed to the arithmetic formula, because with this one, we don't actually care what the last term is, the 6th term. We just need the first term and the R value, and so all these are relatively easy to find. So the first term in this problem was 8. The R value is going to come from doing 14 divided by 8. Which is 7/4. So each number is multiplying by, I wrote plus 24 plus 5, but I really meant plus 24.5. Sorry, that was my bad. Okay, so each term multiplies by 7/4. That's how you get to the next term. 7/4 is 1.75. You can use either of those numbers in the formula, and you'll get the answer right either way. So we're looking for the 6th partial sum, so we're going to say the first 6 terms is going to be the first term times 1 minus 7/4 to an exponent of 6 divided by 1 minus 7/4. And the only mistake I really see students make here is that if they have a negative number for R, or if they have a fraction for R, I see them skip these little parentheses a lot, and then that gives them the wrong answer. So as long as you are keeping that in mind when you plug this in, you should get these right all of the time without a lot of effort. All right, so when I type this in, I'm going to do 8 times, and then to make it look like what's on my paper, I'm going to use alpha y equals so that I can plug this in as a fraction. So 1 minus 7/4 in parentheses, just like I said, to the 6th power divided by 1 minus 7/4. And some students might prefer to type this in using the decimal version of R, because when you do that, you don't have to use parentheses around your R value. It only works if you have an R value that's a nice decimal, which we do in this problem. So we have the approximate answer is 295.711. And I'm going to go ahead and try to turn this into a fraction, and this one happened to work. So anytime you can write it as a fraction, that's always preferred because it's the exact answer. All right, second example, we're going to find the first 11 terms of 7 plus negative 24.5 plus 85.75. I don't know why they came up with all these crazy problems, but it wasn't me, it was the book. All right, the first term is 7. The R value is negative 3.5, apparently. So for each of these terms, if you multiply by negative 3.5, that's how you get to the next term. And we want the first 11 terms, so we're going to say the first 11 terms are the first term times 1 minus negative 3.5 to the 11th power divided by 1 minus negative 3.5. And so we have, I've got to write it before I can pronounce it, 1,501,877.337. And this one did not want to turn into a fraction, so we're just going to leave it like that. Okay, We'll do one more example and then we'll call this video good. So the third example, we're going to use summation notation, but we know it's really just asking for the same thing. It's just writing it a little differently. And this one does not want the first 7 terms. It only wants the second through the 7th term. So instead of finding the first term, I'm really going to start with the second term. So I'm not going to use 1, I'm going to use the second term. So my second term is 3 times 5 to the 2 minus 1, which is 15. My R value is 5. And I do need to know the number of terms that I have, and so that's going to be 7 minus 2 plus 1. So that's 5 plus 1. So I'm finding 6 terms. So the sum of the 6 terms, they're not the first 6, they're the second through the 7th, is going to be our first term, which is 15, times 1 minus 5 to the 6th over 1 minus 5. And that is 58,590.